So you did send to everyone or only to a selected group?
No, well, a lot of them do it. It's not the only one.
Do you need it sent to everybody?
Yeah, it's better.
Oh, okay, okay.
I don't know if this group of undergraduates will come or. Okay. Oh, sorry. Okay. Many thanks for continuing to support the course by coming, which I do not do myself all the time, as you noticed yesterday. How did you like the lab, dude? Yeah?
Really appreciate the printouts. It was very helpful.
Yeah, I liked it a lot. Yeah.
It was very helpful.
Okay.
Thank you.
So did Dr. Han made a little presentation on the screen, or he just let you try it and?
He helped us. He walked individually to our computer and helped us.
But did he present something to the big screen?
Yeah, he just kind of follow along just what we were doing. It was very quiet.
Okay, very good, very good. So if you are not very excited about equations and theoretical part of the course and focusing primarily on the practical part, then most of the lectures you can lean back and relax, right? But not this one. This one will be, comparing to others, it will be one of the easiest, but if you are looking forward to memorize something, it will be the material from this lecture. And I do not care much about like checking and grading, but maybe I'll make a little exception with material of this one. So basically what we will cover is expected to like you can creatively process it and put in the methodology sections of your reports. Of course there will be a little differences, one person does one thing, another, but there are some common grounds and almost a template that you may want to use. So, if we will be in real rush, the material for today can be completed really quick. So we can go in slower, just a little slower mode. So by now I do have, oh, I need to move this stuff. Here, flowchart of DFT computation. And I did put here links to all recordings except the one, the lab yesterday. But I hope it that tech support did good job of recording, so hopefully you'll be able to look at it. There are also recordings from previous years which you have some doubts, you can compare this. So, to my understanding, it is what you were doing last night, right? So, and in order to save time and space, we will not go over practical steps, but so you did learn how to modify the electronic configuration. We are still, like, if you need to list your approximations or limitations, we are still under single determinant DFT theory, and for some of this advanced excited state configurations, it's not the best thing. So we are going the lowest order of precision, but still it unleashes, untie your hands and allow you to do the anions when you promote electron from valence band to conduction band, and if it is chemistry, it will be like reducing catalyst or basic environment, right? So if you just pour hydroxide somewhere, to some extent it corresponds to such situation. The acidic environment, when you remove electron from the valence band, and also these two situations can be used, these two configurations, if you are trying to move towards electrochemistry. If you want to describe molecule on the surface of electrode that is biased with either negative or positive potential. And if it is like positive, if you withdraw electrons, see this red stripe is pulled down from the green, right? The system is missing an electron or few electrons, right? So what you did yesterday, you changed the parameter n right? In car. Here you changed it to smaller value, here you changed it to larger value. And then you did use the keyword Fermi weight, right? You recall it. Which promote an electron from valence band to conduction band, right? And it is a very, very low order approximation for excited state. It's to some extent it is a little better than our tools for linear absorption, because it shows how the electronic structure reconfigures after system is being excited. Okay, and another thing you did was the, how do you call Apple devices if you are using, or your friends are using products of Apple Mac company? Like if it is a cell phone, how do they call it? Yeah. So here the keyword was I-spin. Okay, I-spin equals 2. And then you, so then instead of one list of orbitals and occupations, you have two independent lists, right? One for alpha and one for beta. And this was, your practical example was minimalistic titanium dioxide nanowire, where one titanium was substituted with vanadium, which has one more electron. And it is predominantly open spin, open shell configuration. Number of spins is odd, right? And you do see that in one list of orbitals, there are orbitals that are occupied, but they technically belong to conduction band. And for another spin component, everything is normal. Valence band is occupied, conduction band is unoccupied. So it is also, we are not going high, but it is at the introductory level a reasonable tool to describe magnetic materials, metal-organic complexes, and chemically active radical intermediates.
You saying these are just properties that those tend to have?
Organic, magnetic, and radicals. So your question?
Yeah. So with, you said these tend to be those magnetic
Materials, yes.
Yeah, materials. So are you saying all of them just tend to have an excited set of electrons in the conductive band, ready, waiting?
No, not necessarily, but I like very much the train of your thoughts. What is the magnetic moment of spin, of electron with one spin?
Magnetic moment of spin?
Yeah. Is it a, you always can tell, if you don't like question, you can like, question is not posed in a legitimate way. I do not like how it is formulated, but if you are not against the formulation of the question, you may tell that.
Yeah, what comes to mind is a moment is like a value to me. But
Yes, but do you know the Bohr magneton? Who heard about Bohr magneton?
So you're talking magnetic moment, right?
Yes. So something like I can't pronounce it. Gyromagnetic ratio, gyromagnetic ratio. Can you pronounce it?
Gyromagnetic.
Gyro. I'm slowly learning through years. While teaching this course, third time, I learned how to pronounce the words anion and cation. Before I was doing something wrong. So, gyromagnetic. Thank you so much. Gyromagnetic. Sucks. What's that?
Way over there.
Okay. So, it looks like I'm deviating from the main topic, but since you are interested, the physics, not 100, but like high school or middle school physics, if you have a coil with electrons, with current, right? This coil creates magnetic field, right? And if it goes in a certain direction, then the magnetic field goes through this coil on one hand. So it's source of magnetic field. On another hand, if you apply external magnetic field, this coil will respond to it and turn around. Right?
okay.
So you remember something like
Yes.
this. And now I need to put microphones off. Do not repeat it in public. So spin can be considered as a little charged sphere. This is wrong. It's only for our understanding. Little charged sphere that rotates around itself. Therefore, on the equator of this model, we have a current because charge is moving. Therefore, single electron also has magnetic moment, and therefore it will respond to magnetic field.
Okay.
Okay. But if you have two electrons, they like to be paired in the opposite direction, and net magnetic moment is zero. Okay. So it is not direct logic, but here is as follows: if spins are unpaired, if number of spins up and spin down are different, material will be magnetic.
Yep.
But we can set up a logic in the opposite direction. If a material is magnetic, highly likely it has unpaired spins.
Okay.
Okay? So it goes with this stuff. Okay, and then there are orbitals which are also, for the same number of orbitals, they look very different. They have different symmetry, right? For spin alpha, spin beta, or spin up and spin down. And if you do have access to VMD, it will be very natural. Then you do same as in Gauss view, as for Gaussian results. You just plot spin up and spin down, spin alpha and spin beta. If we do not have access to it, we can do a little more awkward thing. We can plot summation of the charge densities for orbital of the same number but different spins, right? And we can do subtraction. It will be not a big programming effort to practically perform this subtraction, but we are doing some introductory lower level, and we do what we can do easily, right? So summation and subtraction. And since if you would apply this procedure to any non-magnetic material, this closed shell, you'll get something for summation and zero here. Because if there is an orbital filled with electrons spin up and spin down, and they're sitting on the same, they have the same spatial distribution.
Yep.
Then when you subtract, it will be zero. But here, alpha and beta are drastically different, therefore we have some structure. So there is a little reason, and if you did look through recordings that I sent during my absence. You may have seen it, and maybe I will present this once again, a little part of the lecture material on this spin density. So the procedure for density functional theory, when we do such calculations, it uses not alpha and beta, but it uses sum and difference. So it's more native language for DFT. And also, if you're looking at orbitals only, if you give up density of states, if spin density or subtraction of alpha and beta is non-zero, it's also an evidence that material is likely magnetic. Okay. Good. And then a secret thing that is hidden by this screen is absorption spectrum that comes, that you did yesterday, that comes for the spin polarized models. Why we do need it? Can we give up spin polarization approach and do just same orbitals for any system? No. If you apply regular approach for spin polarized open shell things, it will give you nonsense. So if you have your physical, chemical, engineering, scientific intuition that there are unpaired spins, then one needs to tell I spin 2. One can do it every time, but then calculations will be more expensive. Sometimes we just save effort on doing of giving it up. Okay, and for absorption spectrum, like even if it is open wide gap semiconductor, there appear, as you may have noticed, there appear transitions much lower than the gap, like gap about 2-3 electron volts, and you do see transitions at less than 1, right? Because it will be transitions from occupied, which is technically in the conduction band, to the next, like from former luma to luma plus 1, and it will be really small transition energy. Okay. I think you were very tired yesterday, and while preparing these materials, it was interfering with the conference, so we didn't include key points, momentum distribution, which is needed for Kevin. So I'll try to share materials with everyone, and Kevin specifically during remaining day of the week, during tomorrow. Okay, so it was a little review of your yesterday lab. Here are your choices, right? That you are aware about because it was just your free practice of your free will.
Queenie, you misspelled my last name. It's Hedrick, not Hendrick.
Oh, Queenie maybe not in the recording if he's not in the connection, if he's not responding. I saw him today in the airplane. But
oh, wait, he's back on. Queenie, you misspelled my name.
Even if he doesn't hear it, now this recording will be recorded for the history.
Right. Okay.
And here, so do not worry, we have plenty of time and we will finish in time or earlier. So here are the list. I just added a couple of ideas that I've got by talking to you in person, but it's like 5 things. We need 11, so you may want to select subject, and if I didn't mention it, you design it yourself. So there will be 1 copy for your records, and I will put some large symbol on another copy for myself. I know that probably you are worrying and planning to complete your presentations that will be after the weekend on Tuesday, but right after you complete them, we will kind of stop learning and start practicing. So we will go to projects, and it will be really great if by the time of next lab, by what is it, Wednesday, I have some ideas what you want to study as your research project, because we got like just a month to complete everything.
When do you want, like, you want the paper ready and handed in, like, May 10th? Or do you have, like...
Oh, it will be earlier. You complete research in like 2 weeks, then write a paper in 1 week, and use another week for presentations. There are secret procedures that help to do things quick and efficient and high quality. I'll share the secrets.
Okay.
Can you pass it? Hold it. Okay, so you're not obliged to take any of those. If you have your own creative idea, just feel free to write your name and put what you want to study.
So you're saying you want us to name one of the 1 through 22 and something on the right?
No. Select research project that you want to pursue towards end of semester. Right? Research projects that you will explore computationally, highly likely using VASP.
Okay.
But again, it is a disclaimer, it is not mandatory to use VASP. You can use any software, but you know my opinion.
Queenie just told me he is online.
He's online, okay. So
He is.
this will
Must be a mic issue.
Queenie, this periodic polymers is it will be about you, highly like your project. So do not rush to do it this second. I just want to collect this piece of paper with a little star by the end of the meeting. And if you do not see stuff that you like, put anything you want.
He says thank you.
Queenie, you're very welcome. Okay, so what did we do last time? It will be review not only for you, but for me as well. So who we are and what are we doing? We are getting both practical and fundamental practical skills and some basic knowledge about density functional theory, and it is based on two theorems. One is that if you know density, we know everything. Density determines everything. And second one is that there is only one. For the only one correct density, there is only one correct minimal total energy, right? Correct me if I'm misspelling or misinterpreting something. You may have fresher knowledge if you were reviewing stuff. And based on these two theorems, one is developing an algorithm for practical solution of electronic structure problems for molecules and materials. So when we were here in the previous meetings, we went over the concept of expressing energy of electron-nuclear interaction in terms of external potential. And this idea, just practicing some little manipulation, brought us that external potential can be reconstructed from energy of electron to nuclear interaction through the mean of functional derivative, right? So same as regular derivative, but with Greek delta, which means you vary not one variable, but three-dimensional distribution. And then we did discuss that based on the theorems for available density, one can find correct total energy. absolute minimum. But theorem doesn't tell, doesn't tie our hands about possible manipulations. And there is an idea of designing an auxiliary universe where converting density into total energy is much more pleasant and easier. And this auxiliary universe is equivalent to real universe. So in the auxiliary universe, we remove electron-electron interaction, but in such way so that total energy obtained from the total density doesn't change. So we just rescale, give a little bit more power, a little bit more value to electron to nuclear interaction in this auxiliary world. And this is an important technical step because we remove electron-electron interaction, which gives drastically substantial complication in all calculations. What else? We are not literal followers of the density function theory. We give it up for kinetic energy. So we use more standard, more typical approach for kinetic energy, and therefore we exclude kinetic energy from the total. So if you do know, if we already know total energy out of density, and we have additional way to compute kinetic energy, then this external potential is functional derivative not of the electron to nuclear interaction, but subtraction of total energy minus kinetic. And we do not have electron-electron. In the auxiliary universe, the type of this potential is later on we will discuss, is made in such way that it does mimic a realistic universe. Why do we care about this external potential? And it was the next subject we covered. So if this external potential, if the electrons do not interact, then this external potential equally acts on any electron, right? Because it is only interaction with ions. And then we can jump from, if we are in this auxiliary Kohn-Sham universe, we can jump from multi-electronic problem with many electronics Cartesian projections as independent coordinate to independent one electron orbitals. And this external potential will equally serve each of them. So from one multi-electron equation, we go to many one-electron equations. But later on we discover that they are the same. And as by the shape, by functional form, it is same as Schrödinger equation. But because we use something different from a regular potential, we call it Kohn-Sham equation. Because this V is not realistic, it is like abstraction. So those are Kohn-Sham orbitals, and those are Kohn-Sham potential. And the wave function for the ground state in this Kohn-Sham universe is expressed as Slater determinant of all occupied Kohn-Sham orbitals, right? And there is a trick that we considered here in this audience, that if we carefully process Slater determinant of multi-electronic wave functions and express multi-electron density, and then project it only on coordinate of one electron, like making summation of all but one, then the density as function of one Cartesian, one three-dimensional, three Cartesian projections, is nothing but probability distribution or density distribution for each of the orbitals. So we did a proof for this stuff before, right? And what we did here in class was for 2 electrons, but generally it is a summation for all occupied electrons where this index I goes from 1 to number of electrons. And if we are speaking of spin polarized calculation, then we just put here alpha, number of alpha electrons, and do summation I from 1 to number of beta electrons, and put here theta I beta squared, of course as function of r. Right? So we do have all components that are needed to construct the computational procedure, to write a code that will do these calculations.
Looks nice.
It's something that I previous year I was asking class attendees to go one by one and write equations, but maybe we can skip this procedure to next year, because you already have hard life and you do so many assignments. But what can you show it once again? Very interesting. Nothing wrong. It's good. It's good. Yeah. Yeah. Very good. Very good. I'm very pleased to see that some of the class attendees are taking notes in a careful way. And I remember from my little experience, the best way to inspire anyone to take notes is tell there is nothing important, just do not write, and then everyone starts, oh okay, probably I should take notes. So everyone remembers Taylor expansion, right? I think this is a little comment that I just briefly mentioned. So if you have a function, it can be represented as value in a given point, and then plus derivative times increment from the given point, right? So same in the functionals, you can express this external potential as total energy. They are connected as LDA, which we covered through Thomas Fermi, as integration of density at all points of space with some power, plus additional integral of the gradient, first derivative of the density. And those are two letters of the precision in the density functional theory. LDA only, and then GGA when there is a gradient here. Okay. And this is just repetition of things that we had. Like Kohn-Sham equation, combination of the total density out of orbitals. Okay, let's check if you were feeling comfortable going over these equations. So you do not need to return these quizzes immediately. There are two sides, so please start filling the front side right away. And there is a flow chart on the website that I will instruct maybe in like 2-3 minutes how to do.
I already did the flow chart.
Huh?
I already did the flow chart.
Okay, good for you. So do not develop irritation against the instructor. Do not think of this. Keep writing. I'm just mumbling. Do not put too much value into this exercise in sense of grade, like do not, but try to do it carefully with the following motivation. Later on, you will need to write methodology section for your research projects. There will be guests on the presentations of the projects who may ask what is the essence of your methodology. There is not very likely, but not impossible situation when you go to like department store to buy like fruits and bread. A stranger catches you and asks like, explain me which theorems are behind the density functional theory, and you may want to have the reasonable answer. So there are a couple of key features, key concepts, and like total energy, potential, one electron equation for orbitals, density composed of orbitals, and you can try to reproduce it either based on your memory, or if you were taking notes, I don't mind taking it from the notes, and then do brief explanation what are the benefits of this. I shouldn't show it. Okay, and try to write down your explain what are the benefits of this equation to your best understanding, but don't waste too much time on it. Just briefly. Only 1, 2, 3, 4, 5. Good. So let's help each other by doing it collectively. So maybe starting from David.
Yeah.
You just go and fill one cell in this table in public, and then return to your place, and then you go in sequence.
Okay.
And since you're the first, you can choose which one to fill.
Yay.
So there is like finger writing. I think.
Yes, this was review last lecture, 20.
Excellent. Yep. Okay, Gage. And you can either put an equation or just add some benefit that you think is appropriate for one of these concepts.
I think I can focus on.
Okay.
Okay, back.
Escape on the keyboard. Okay.
Okay, it's supposed to be a 2.
What's that?
Ah. Probably erase.
You can just cross it out or select it.
Oh. Okay. had something.
No, just
no,
write
no, I had
this.
something written down.
Let's do it together. So which letter for potential?
I thought I had E involved there.
Huh?
I thought I had E involved there somewhere, not necessarily.
I would use V. Lowercase. Okay.
Yeah, no one can tell.
Okay. And is it related to total energy and kinetic energy?
Is that P like density P? That's wrong. We're like, yeah, that's
So it's like functional derivative.
Is there a DR and a DR prime involved?
Well, it's like a fraction and delta on the top and bottom. Okay. And here it is density, and on the top.
I don't think I'm doing the right equation then.
But you can try it right now. We just had it on previous slides.
So we did.
So we do not have electron to electron interaction. We have only electron to nuclear and kinetic. So total energy is electron to nuclear plus kinetic.
Doesn't it come from the total energy equation?
Huh?
Doesn't that potential come from the total energy equation?
So what the equations that Gage will write in a second includes total energy, but I'm avoiding specific expressions of total energy because anything except LDA is very lengthy. It will be like taking several pages of equations. Just there is a subtraction of two things. One of them is total energy and another is kinetic energy. Excellent. Yeah,
Yeah,
that's correct.
Let's say that's legible.
Yeah, that's correct. Kurt always wanted to go to the station and write an equation.
Two computers. Because one ran out of batteries.
Yeah, can you hear me? I have a question.
Yes, I'm listening.
Okay, so V is equal to the derivative of an orbital with respect to momentum. Am I understanding that right?
Please repeat once again. I think I understand what you mean, but just once again.
So V is equal to the derivative of an orbital with respect to momentum. Is that what the potential equation is saying?
No. Yeah, this you mean this symbol?
Yeah, the V equals.
V equals functional derivative of total energy minus kinetic energy
Okay.
and the total density in the denominator. More traditional letter is T, like in a lot of literature, but we are free to use any. And a question that Mary did ask, you can just write down that it is a functional of density. Right now we do not need to be specific. Okay?
So the potential is the derivative of the total energy minus the kinetic energy with respect to density?
Correct, absolutely correct. Functional
All right,
derivative. So you either add something here or equation for orbitals.
I think I could change it over the other ones.
Well, total energy is good because is important because we need to minimize it.
Minimize. Minimize this computational. Or?
No, just write word minimize. Escape. Okay. It's good. Thank you. Haha. So, Ben, I guess he wants to put Kohn-Sham equation.
This is the touch screen, right?
Yes.
Okay.
Okay, thank you. Everything is correct, but I do see that Ben did selected an easy way to avoid explicit expression for Kohn-Sham Hamiltonian, right? So, do we have a volunteer with first name Nathan and last name Walker to put explicit expression?
I can't remember it.
Please try. I'm confident you can.
I really can't remember.
I mean, come on.
There's no pressure.
There is no pressure, but Hamiltonian always consists of kinetic and potential, right?
Yeah.
And let's keep the constants. And there is a very important thing, that this V does depend on R as function, and does depend on what as functional? Rho. Rho. Okay, very good. Thank you. So this V that Nathan has introduced to us is not independent. It does depend on the density, right? And through the equation that was provided by Gage, right? And this well, this is not complete equation. It just shows the dependence. So the total energy depends on density. Density enters into this subtraction and functional derivative and gives potential, and potential enters into Kohn-Sham stuff. Okay. So it is what was written by in previous years. Good. Now, the favorite subject of CART, flowcharts. You know, some people have skills to program. Some people just need the suite of codes for applications. And but if you have new idea and you need a suite of code to follow this idea, and you don't have time, but you have like lots of funds, you can hire professional programmers. But you still need to explain what needs to be done. And these flowcharts are like oversimplified language for ideas, like which procedure follows which one, how they are connected. And we are going to summarize the procedure for Kohn-Sham procedure for finding total energy in form of flowchart. So I suggest that you do flip. So you did this one. You flip your it's not very visible. Pages for the quiz, and if you have already written something, it's really good for you. But there is no expectation for all of us invest so much time in writing equations, so I prepared some stickers. So there are total 7 stickers, and there are total 7 cells. I have several sets, but you need one sticker of each type and apply it to the right place. If you do not know where to place it, you can just detach sticker from this field and pass it over so that we save time. Oh, you already got it.
I got one of them.
Okay, now you have 3 things. 1, 2, 3, 4, 5, 6.
I have 10 fingers, so.
I think these. No, you already got it. Only this one. Yes.
I like this sticker idea.
Me too. You know, at this school, both activity of students and faculty is evaluated, and I really wanted faculty evaluation will be done at the lecture when stickers are used.
I'm sad I'm not there. I would like to see the sticker.
I'll save a set of stickers for you.
Oh,
You can apply to like a refrigerator.
That's right.
I like that.
This equipment works.
Alright, where do we start? Which finger? So that's
what's bothering me. Slanted.
Alright,
I can't figure it out.
that looks too complicated. This one, I want to say it starts with this one. So do you want to start with the folder?
Let's see.
So, Sudipta didn't approach the board yet. Can you please come and put one of the stickers in public?
Okay.
Anas and me, you will be the next. So just put one of the stickers and try to put it in the right place. So the idea is that we start from input and end with output.
What will be the output?
Huh?
What will be the output?
So what is the question of Sudipta? What is the output? What is the main goal? What is the main output of the DFT? And any electronic
Observables.
structure? Observables it is more advanced, but on the lowest level. Any ideas? And you have choices. It's like multiple choices.
Final energy?
Yes.
I'm choosing yes. Okay.
Excellent. Yeah. Thank you much, Sudipta. So total energy which depends on positions of ions and total number of electrons. Anas? Please come and help us.
Yes, stickers.
There is another set. You don't need to take anything with you.
You guys do stickers?
No, I haven't.
Have them all?
So many.
7.
So, what is the input for any electronic structure? Well, you can do anything you like. If you have ideas, follow them.
Can we shout out an answer?
Okay. Anna selected the no, not on the screen. Right in here on the paper. No. Let's discuss. So it is a comparison of the difference between total energy at different steps of the algorithm with the tolerance limit. So
That's in the mid-
it is the like algorithm for. He's debating this one.
That would be like in the middle somewhere. That wouldn't be in the beginning.
So what?
In the triangle thing. Oh, the parallelogram.
Can you please repeat once again?
I think it should be in the parallelogram at the very bottom.
The diamond.
Oh.
So it is a forking. When you see most of these blocks have like one input and one output, and diamond has one input and two outputs, right?
Yeah, I think it should be in the diamond.
Yes, excellent. So, thank you, Anas. Mead is going to come and impress us by filling one more area. So what are you going to place? Okay, total density. Good choice. It's like shocking.
So I'm gonna assume it's somewhere in this area. I'm gonna say it's number 2.
Okay, you can place it here, and it will be not wrong. Yeah.
Oh,
Yeah, thank you. But there is a little ambiguity. So here I do not have this row without equation. So in fact, we use it twice. So there is a little thing that we may discuss when we go through this set of equations. We need density in order to find potential, right?
yep.
Equation is somewhere here. Yes, this one. But if you didn't start to solve any equations, where do we get density? So in order to the system to start working, one needs some initial density, either educated guess or just random numbers. And therefore, the input includes also something trivial, like positions of ions, and just random density.
So it could have been anything.
Yes.
Generally in the
Yes.
field. So just for our stickers, I know we're missing the regular one with that just as density.
You have
It would been.
another sheet with only one line of like row equation.
Yeah, would it have been here then?
Is that row without an equation
Yeah.
like a random
Yeah,
density?
yeah, it will go here.
Okay, right there. Thank you.
Yep, thank you. So others were already going here, but probably Kurt wants to practice another public activity.
I can take a shot at it.
Well, stickers are easier.
I can go after Kurt.
You know, there are. Keep yours with you.
I was gonna just.
So each algorithm has input and output. So what's the input for this electronic structure. Positions of ions, right?
Right.
What?
I thought we input density.
Without positions of ions, chemistry doesn't make sense. You need to define your model, right? Absolutely correct. Yeah, thank you. We have 2 more volunteers. Okay, I will be a proxy. Mary wants to place one of the stickers into one of the cells. Yes, what are you thinking about?
Can I see the options? I have a 50-50 chance, right? Okay.
So we did play into Wheel of Fortune. I don't know how to call this game, but you should rename the course.
So the far 2 stickers on the top, like, yeah, like there,
Okay.
and the one next.
Well, just
So
one.
One.
So, Kohn-Sham equation or equation for potential?
Let's do. I want to say potential.
Okay. So, and now, by free will of Mary, the potential will go either one or another cell. What goes earlier, potential or Schrödinger equation?
The Schrödinger equation would go earlier, I think. So potential should go in a second.
Other alternative options?
The other way around.
To write down a Hamiltonian.
Huh?
Need a potential to write down a Hamiltonian.
So, first or second?
Second.
First.
So let's vote. How many for second? One. How many for first? Okay, by majority of voice we apply it here. And credit goes to Mary because she initiated the activity. Okay. So, and the Gage wanted to put the last one.
I suppose I can do that.
Okay.
Did you mess up? Let me see. Let me help you.
I think it goes right about there.
Okay, excellent. Thank you much. Okay, I put here just the whole class. Collective. So I don't know if you need much of grading, but I'm going to collect as a good memories.
I just throw him on the
So we go from input to output, and as soon as we have density, we go to potential, Schrödinger equation, and redefine the density that is used again. Yes? Yes? I think everyone performed so perfectly.
Thank you.
Thank you.
Thanks to our teacher.
Good. So, and we will not write down handwriting in things as we did in previous years because you know how to do it. Oh, okay, so here's the answer. So, what should we think about? Like, how can we analyze and connect it to our practical activity? Most of you may not run into the numerical error that I'm going to declare, but I promise each of us will run into it once or more. So you notice that if you do orbitals and if you do absorption spectra and orbitals, first you need to do previous single point optimization calculations that gives you non-zero healthy wave car, right? Did you ever try to run specific template of the in-car file for the orbitals in the empty directory where you do not have wave car? Okay, because you are so educated and smart. When I was learning the software, I tried it several times. So it is an error. If there is no wave car, there is no reason to find orbitals. But if you try to do it, it will be like garbage. You feel a little clouds at each side of the simulation cell, which shows how WASP generates random density with random number generator. And it is an important observation for those of us who like programming, or for this part of us that is inclined to programming, that it doesn't matter from which initial starting point we start, the algorithm will give us the correct answer anyway. So you start from absolutely random distribution of densities, and through these iterations, it will give the right answer. It's really impressive. So result doesn't depend on starting point. Like when you do wet chemistry, if you start with wrong components, you never get right answer. Right product. What else? And another interesting observation that here, see, the total energy depends on position of ions and also number of electrons. So it was the first section, or section number 0 in your lab. Anions and cations. You have the same atomic model, same number of ions at the same positions. You just change number of electrons, and your total energy and density of states and all observables do change, right? There is one more thing that was just kept for brevity, but also there is a spin polarization, number of alpha minus number of beta, which is WASP keyword and up down. We'll cover it hopefully once, which is important for several for configurations with different spin multiplicities, like singlets, triplets, doublets, quartets. It also, you can have the same oxidation state, same ions, and just change spin configuration and get different total energies and different density of states. Okay, so another thing, what is the benefit? How do we use this algorithm? Of course, we can take this flow chart and sit and program. It would be possible. Anyone who is in the process of getting Bachelor of Science degree or already got it is able to run create DFT code with maybe little instructions of how to record equations into programming language. It's not a big deal. We're just skipping it for time aspect. But is it the only thing that we can use this Kohn-Sham DFT algorithm for? Is there any connection to other activities, other computational tasks we do in the class? You are very welcome to stop me and give your own ideas. So, and if there are no suggestions, I'm going to make a couple. So, when we were at the beginning of the course, first month, chapter 1, we looked onto optimization. And we considered force field, right? And you probably remember this flowchart. When each of us pretended that we are small computers that want algorithmically find the minimum of harmonic potential. So in the force field geometry optimization, we do use information about potential or total energy of the system as function of positions of ions, right? And we told that it will be provided from somewhere, or it is tabulated somewhere if it is force field, or it is recomputed. So now it is time to make this connection to the beginning of the course. So at each position of ions, we can compute total energy and use it as potential energy surface for optimization or for molecular dynamics. So just in case, let's refresh memory. So it is also a flow chart, but it is different. By now we had 3 flow charts: optimization, Hartree-Fock, and DFT. There will be number 4 in 5 minutes. Prepare, and you may like it very much. It will be connected to real practical life. So recalling our flow chart number 1 from chapter 1. So one starts from initial geometry, tolerance, time step, and then if we didn't expire our computational limit for wall clock on the cluster, we are computing the gradient, right? And multiply the gradient gives us acceleration, right? Force, acceleration, and we multiply it by delta t squared according to Newton's equation to see that positions of ions will move in the direction of gradient, right? And we assign increment of positions. Then we go a step forward from position number n to position number n+1 according to this increment. And then at new position n+1, we recompute the potential. And when we were in the chapter number 1, we told like, this part is a black box. We don't care where we get the potential. Right? But now we do have a tool that you guys have just completed. You have a tool that converts positions of ions into total energy of system. So if you change positions of ions, you have different total energy of system. Right? So we do have black box. So your completed quizzes can be just pasted here. Make sense? So we will have one cycle, and then if it converges, you report minimized geometry. If not, you repeat the whole procedure. But now you have one cycle for minimizing the geometry, and inside another cycle for minimizing electronic density and finding electronic energy, right? So like 2 cycles laid inside each other. You like it?
Why have you been calling it a black box? Because
Big black box. Well, there is a brand of wine, black box. But black box is like concept, a keyword which is taught, which is used when I want, like, I'm telling that I'm using black box if I'm user of something. If I don't care how it works, I need just to provide input and get output.
yeah, but I've heard other people like have presentations with the black box, and I'm just kind of curious why that's okay in academia. Like, yeah, we don't care how it's done. As long as it's done.
It is, of course, in academia we are expected to be curious and dig down until we understand all details. But on the other hand, there is a divide and conquer idea and strategy. You can, with limited lifespan and time, you cannot be super professional in everything. You need to delegate some of the activity to other people. And you assume that someone does portion of the assignment and give you answer. And you don't have time to learn how it goes, and you assume, okay, it is a black box because my companion is doing it.
So someone knows.
Yes, yes.
Perfect.
It is not black box for the whole humankind. It is a black box for me.
Yeah, I thank you for explaining that. Because I was lucky to miss that.
So if you are involved or plan to be involved in programming, there is a concept of subroutines, right? And you may write your subroutines for yourself, or you may borrow subroutines from the library. And even if you are a very responsible programmer, sometimes you do not have time to read what other people wrote in subroutines. And some subroutines are coming like a packages which are already pre-compiled.
Yep,
You just need to learn what is the input, what is the output. So the subroutines are a lot of black boxes. Okay. Kurt may correct me if I was.
No, that's pretty much everything I do.
Okay. So black box. It's really black.
Yeah, it's kind of like using an equation, but you don't know how it was made, sort of thing, right?
So we are going to paste our CHEM algorithm inside of this procedure. And now, so before, if you would follow just your little quizzes, you would be able to write a code, or if you hire someone to implement it, it will be only the code that for each position of ions, for each molecule, generates electronic structure, single point. If you create wrong geometry, it will give you a wrong answer. So it will be not very efficient for practical aspects, because human hand is not able to draw things ideally. It would work only for structures borrowed from X-ray diffraction .cif files, right? But many of practical molecules we work with do have unknown or slightly some structure with some level of uncertainty, right? And then we do need to practice optimization. And then we use, it is what implemented both in Gaussian, VASP, and other like pieces of software like Quantum Espresso, or ACES, whatever, HyperChem. So you insert geometry and tolerance, and then you start optimizing geometry, but for the gradient, maybe even these boxes need to be swapped, you launch your protocol, your self-consistent algorithm for DFT that generates your total energy for provided positions of ions. And then you check if the positions of ions computed in the next step and previous step were smaller than tolerance. If no, you go across and optimize. You slightly change positions of ions. And for new positions of ions, you go through the internal cycle for electronic structure. When it is converged, you go again, and you complete it until everything converges. Okay? This is the main idea of today's meeting. Well, second main idea, and it is maybe flow chart number 4. So, did you look into I'm not sure, OZCAR file? Huh? So when you do VASP calculations in your directory, you can look into OZCAR, and it does show you progress. Especially it is interesting to look there if the job is not completed and you want to watch it. Or the content of this OZCAR or similar content comes out if you are avoiding using queues and directly running, not submitting a job, but running VASP interactively. You type the command and then something develops on your screen. And it looks approximately this way, right? So it is interesting that there are two counts. One count, din din din, very short, and then it gives energy. And then there is another count shown in blue. 1, 2, 3, 4, and so forth. So these little counts are electronic iterations. And here is the like tolerance or second derivative, change of tolerance. When it gets to the small number, the electronic cycle is converged and total energy is reported. And based on gradient, ions are shifted. And then at the next position, it again launches the electronic cycle. So in this example, it was really quick, very nicely converging, but sometimes it may go for like 10, 20, 60 electronic steps, especially if your initial guess is not very good. So, cycles, electronic and ionic, right? And you do see it in practice when you do this little lab works for practical session. You know everything, right? So if we are not targeting top-level precision of calculations, if you're not looking for like 5 significant fix corresponding to experiment, you are already accomplished computational chemists. You can go into projects. Of course, there are little things we can give more details. It is the one that I was sending as in recording, and that I will probably present in a week after your presentations, explicit shapes of the functionals. And we can go and overview other theories that give higher precision compared to DFT. What else can we do? We can look in more details on possible observables and ways of comparing to experiment. But by now you do have solid background that allows you to take any geometry of any structure, any material, any molecule, and both find its electronic properties and like through molecular dynamics see how it does respond to the heating, right? So if we would decide to go deeper into theories at this point, everyone in the audience would get maybe too much exhausted and tired. The best learning is by doing, and maybe after you do presentations about VASP skills, we should immediately dive into practical projects so that you do not lose enchantment and enthusiasm and immediately apply this basic skills to some realistic systems. And then after getting this experience, we can add a little bit here and there to be more accomplished, to have more accomplished arsenal of tools. Yeah, thanks for investing your time. Do not hesitate to please send me reminders, request materials if you need help towards your presentations. Right? So I would appreciate the accomplished PowerPoints on the night before, like midnight on Monday, for your Tuesday presentations, so that I will print them and bring, and everyone can use them as learning material. Did you get the choices for projects?
Watch my house, so you're gonna
A brief question about my presentation.
Ben is going to ask a question right now, and then I'll go remote to remote session. Yes.
Okay, so I was just going to ask what exactly you meant by scripts, because scripts is one of the things that you want to cover in the...
Oh, not research, but...
No, not research.
Okay, yes. Yes.
The ones on Tuesday. It's like scripts and Corey and Photon and...
Okay. How do you submit Gaussian curve? qsub script.pps. And the contents of the script, you can vary it and do different things. And there are scripts for VASP. On Ori, they like this debug dash or Ori dash debug 1.sh. And you can look inside and check what you can modify and look on the NERSC website where they provide some that are helpful. And you can also look, there is a web page on the Thunder, and they give templates for scripts that will launch Wasp.
Okay.
There are different queuing systems on the C-Custody's PBS
No, and I really wish there was more than just me.
Nurse Credit Form.
That reminds me, I need to go back and.
For us as simple users, it doesn't matter, but for professionals like Kurt, it's a big difference.
And then, what exactly do you mean by waiting? Like, just wait.
Oh yes. You submit. Thank you much for checking about it.
Yes.
If you are submitting a job to a queue, it will sit in a queue for a long time before it starts executing. But there are some tricks that
I'm sitting in
how
class
you
right
can
now.
start it earlier. Like if you request only one CPU only for 30 minutes, it probably will get much quicker. And there are specific queues, like there is a debug queue, there is long queue, and depending on which queue you're submitting, you get errors.
I'm just used to.
So just little introduction, because as soon as we get to projects, we need to have high throughput, productive jobs completed, and we all are humans. Our patience is limited. Some people cannot wait. Like if I'm submitting my job and it doesn't start within 1 hour, I'm dropping the course. And I'm like assassinating the instructor.
Up to you, I guess.
Well, I hope you have different feelings, but
I've waited weeks for jobs to go through.
But it means you have very calm nature and passion character, but it's not for everyone. Like some people start like breaking porcelain plates. Like if my job doesn't start next 15 minutes. Yeah, you too. Okay, I'm ready.
Okay.
Mary was next to ask question, but
Actually, if you guys want to go before, because we're going to talk about research, so if you guys want to go before, whoever needs to go.
So you want to give Sudipta a chance to ask his question quickly?
Yes. Yeah. Go ahead.
Okay.
I'm not in a hurry.
On next presentation, I will have to present on DOS and PDOS, and you told me that you.
Yes, we should talk in person. I have some ideas, but you may send me like coordinates of your favorite file. Better the smallest one, and I will develop some suggestions what you can do.
Like I will send you the poster.
Yes.
Okay. Sure. Thank you.
Yeah.
Okay. So, do you want to talk now, or did you want to meet at a different time? Which is
Let's
better?
briefly talk now, because time goes by so quickly.
Right, it is going by quickly. So I sent you a spectra for the wet case for the epoxy. For the new ones that you've run with not the molecular dynamics, but the one, well, there is molecular dynamics, but there's several different ones. What are you kind of thinking? So like running density of states and absorption spectra for all of them, which I can totally do. I just want to make sure the direction.
Do not commit too much efforts before we talk, because it could be a waste of your personal time. So I did try some preliminary calculations, and the model, which looks really nice and reasonable, that you were processing and presenting on the poster, is a little bit, has some problems. So we did squeeze it so much that if you try to process further with optimization of molecular dynamics, it just gets to numerical instability.
Okay, there might be too many. Well, okay, I just want to say, I didn't mention this because we hadn't had a chance to talk, but the density is a little high. The density reported for epoxy in that kind of setup would have like a 1.2, and I calculated a 1.6.
Okay,
So we
maybe it was too much of pressure applied to it, and it starts when it is too much compressed. It may come to like compression-induced degradation. So something maybe could be wrong.
Okay.
And what I suggest as a much safer approach, it's less productive, but we are on the safe side, to restart, like draw back several steps and start from stage of polymerization. So like stick together a mix of precursors of these monomers, water, and heat them up and watch them polymerizing.
Okay.
This could be like, you decide what is better for your project, but I suggest that it could be more healthy approach, because it is not over compressed, and even if you have less results, it is more like canonical procedure.
Okay.
So what typically happens, if you heat the model to room temperature and let it wait for like hours, it will polymerize anyway. But we do not have hours. We can model maximum a picosecond or like 10 picoseconds at most. And in order to overcome potential barriers of reactions, one often overheats model above room temperature. And sometimes reaction doesn't go or goes when it needs to wait too quickly. But then there are ways to catalyze it by changing total number of electrons, which means making it in basic or acidic environment, and it may shorten time from. Kurt, you do not have questions today. Okay, send me emails if you need to discuss something.
Well, it was, yeah.
Okay, so one can shorten waiting time before reaction happens from like hours or nanoseconds to like 10 femtoseconds. There are some there are some reactions that are catalyzed by acidic or basic environment, and it goes really well. And it's simple enough idea that one can vocalize, verbalize, and it is easy to test, right?
Okay, so silly question. When you're doing, this is the anionic setup that we just did in this past lab, is what you're referring to.
Yes.
Yes, that's what I thought. Okay.
But there is a thing that stop me if I'm telling too much or something strange. But I'm kind of considering it self-evident, but it could be not. So please keep under control. I suggest not just simple single point for anions and cations. I suggest molecular dynamics in anion and cation environment. So you take the in-car for molecular dynamics and you add there a keyword that modifies your number of electrons.
Right.
Yes. And then you see how reaction goes if total number of electrons is bigger or smaller.
Okay. We've already done this, right?
No.
No, we haven't. We haven't done this.
No. The model that you are discussing, it's already heated to some crazy temperatures, like
like really high
1,500. Yes.
Yeah.
But for again, because of limitations due to human patience, it could be a right figure to start with. And you see that there is only very few instances of reactions, like opening this epoxy group. So one needs to wait like half of a picosecond before it opens, and we need, after it opens, it needs to polymerize. So this neutral system is a reference point. What if we repeat the same molecular dynamics with less or more electrons, and less and more, not by 1, but by like 20. If it will be like highly acidic, to 20 electrons less. And then we can, systematically change, like do 20 directories and remove 1 electron, 2 electrons, 3 electrons, 5 electrons, and do like this 20 threads of molecular dynamics and see which one is more productive.
Okay, so to kind of go through the files, where should be my starting point so I can like move things to the right directory?
Let's this is better by emails or personally through this
emails
video.
would be great because that way I can know where to start. The molecular dynamics. So I kind of just follow what you did with the first one, but change the keywords that I need to look at to change, and then I create those subdirectories with those different electrons, and then we can analyze that data looking at the what we've been doing in class, looking at the that kind of thing, right? Am I understanding it?
Yes. Yes.
Okay. Perfect. So yeah, I just want to make sure I'm grabbing the right file, and I'd be happy to do those runs, those computations, because we've already discussed it, right?
Yes.
Discuss all the details. It's just the keywords would be new, or they'd be different.
Same keywords. So you take template of the in-car for molecular dynamics, and you just add one keyword, and elect equals, and then you put the number of electrons you want. Before you start it, you need to grab the number of electrons in the neutral system. You just do grep and elect and then out current. It will tell you like 1,000 electrons. And then you...
Okay.
Make sense?
Okay. Yes, that makes sense. So yeah, let's, I can start doing that like tomorrow and then over the weekend.
Oh, yes.
But yeah, if you could send me like just to make sure I got the, if that's okay, would that be okay? Like just
I would appreciate reminders, and we highly likely will have group meeting tomorrow, like from 12:30 to 2 in LED 209.
Oh, okay.
If it doesn't conflict, I can just send you the schedule, and you can either attend meeting or just come after if you are busy with other things. And
well, no, I just have a doctor appointment at 1, so I can try to make it.
Then after the doctor appointment, because before everyone will be busy listening to the speaker.
Oh, okay.
Aaron is giving physics seminar on Monday, and he needs to practice.
Okay. Yeah, let's talk. Would 2:30 be okay? Just right after the meeting.
Let's pencil this time and send each other emails if something happens.
Okay. I just want to make sure I'm looking at the right thing. So all the directions that we were given in lab is everything I'm going to need.
Yes, you do not need anything else. They are sufficient.
And well, okay, so not to be confusing, but when you said this, you called it the spin polarized DOS. That's why I was putting that name on it earlier, because I was
it is density of states for alpha and beta spin components when you say I spin equals 2. For the project that you are planning to do, likely it is not needed.
Right, so the one that's relevant for this one is going to be the...
And you are using the term spin orbit in some aspect that was sounding wrong.
Okay, that could be very
it's not a complicated thing, and if you look in the repository of templates, there is a template of in-car for spin orbit, but we are not covering it in the class because it will be like pumping too much weight, too much time.
Okay. So really what I need is the preparation from the first or the section 0 on the anion, cation, and excited state. That's the one I'm going to be looking at.
Anions, cations, and molecular dynamics from previous.
Yep. Okay, perfect. Excellent. I think that's all my questions now. And so just go where you have the molecular dynamics of, just pick any temperature.